So yeah, thanks for joining us again. My name is Dylan Stern with the Delta Science Program, Delta Stewardship Council. You found us today at the second seminar in the Delta Research Award seminar series, and we're very excited for the seminar that we have planned for you today. And today's theme is migratory fishes, science tools to inform management and recovery. Please go ahead and add your name and affiliation in the chat so we can all get to know each other a little bit better. And the welcome poll should be visible to you. Please take a moment to fill that out. That's really just so we can make these better for everyone. And we're just gonna wait probably 2 more minutes for other people to join us. Just so everyone knows, these seminars are recorded and they're going to be posted to the council's YouTube channel. There's the one from last week is already posted online, and the whole series will be posted on there. We'd really like to encourage your participation and discussion throughout this whole seminar. So please write in the chat box with your reactions or comments or questions. You can also add your questions to the Q&A box, and you can also raise your hand and I will promote you to speak, and then you can unmute yourself that way. All right, pretty good. So I think we can go ahead and get started. So first, I'd love it if Eva could introduce herself really quickly. She's leading the seminar series effort as the Sea Grant Science Communications Fellow. So go ahead.
Hi, everybody. Thank you so much for joining. This is really awesome, and I'm really happy to have participated in such an interesting and great program. Thank you for being here, and please, if you have any questions or comments, put them in the chat and participate. We really want as much interaction as possible, and give praise to these great presenters. Thank you.
Thanks, Eva. Yep, and thanks our wonderful presenters for joining us. I think just really quickly, again, the seminar is open to the public and will be recorded. The format today is that we'll have 30 minutes for each presenter to present their talk and then immediately answer questions. And we want to, again, encourage participation from you. So please add your chat and questions to the chat and the Q&A box. And you can also raise your hand and I'll promote you to speak. Please take a minute to fill out the poll when you see it at the beginning and the end of the meeting. And I will now hand it over to our Delta lead scientist, Dr. Lisa Marie Winde-Myers. Take it away. Thanks.
Thank you, Dylan. And yeah, happy Pride Month, everybody. It's exciting to have another one of these series starting, another one of our seminars in this series starting today. And we'll have them, of course, through the month and into next. I want to highlight that science funding is a core part of the Delta Science Program mission. The Delta Research Awards is just one of the primary mechanisms that we use for science funding. And the 2 projects today that we're going to be hearing about were funded by the 2020 DRA and addressed critical knowledge gaps that were identified in the 2017 Science Action Agenda. As an aside, we're currently operating under the 2022 Science Action Agenda and soliciting proposals for the next round of DRA funding and for the Delta Science Fellows. So the purpose of these workshops is to directly connect scientists with managers and others who might use the information. The seminars are open to the public and are all welcome, and we're especially encouraging conversation among anyone who might use this information. We're going to have time for questions after each presentation, so please add your questions to the Q&A, as Dylan has already pointed out. One of the ways that we track how Delta Science is used is using the Delta Science Tracker. It's a tool to improve coordination and collaboration of science activities, so I also encourage you to take a look at that. So I think we're going to give you a just sort of a preview next of the talks that are coming. Again, we have today a focus on migratory fishes, but we'll have a series, another 5 after this particular session. And if you want to scan the QR code to receive our email announcements, or anything, you're welcome to find more information about these projects, as well as the schedule. So next, let's talk about some highlights that we want to make sure you know about, things that are should be on your radar. One is that we posted an essay about grand challenges, and the idea is to look at what are some of the ways that we can improve science planning by understanding what the big challenges are in the Delta Science program. And so I should say the Delta Science enterprise in general. So it's open for public comments right now. Please, again, go into our website if you'd like to take a look and make comments. We really encourage community feedback there. Abstracts are due for the Bay Delta Science Conference next Monday. I hope we'll see many of you there, hopefully in person in Sacramento. And then applications are due for the Delta Science Fellows on June 24th for the next round, the 2025 round. And the Science for Communities workshop will be held July 12th. And that's a new initiative to, again, be more collaborative and bring science to communities for action. So with that, let's go to today's presentation. And we have today, I'm trying to get my screen to show this fabulous thing. And basically we have today the first presentation, which is science tools to inform with the theme Migratory Fishes, Science Tools to Inform Management and Recovery. We have today Malte Willmes and Flora Cordoleani, and both will be presenting on the effects of climate change on the life history of spring run Chinook salmon through time. So thank you both. I see you both online and really looking forward to your presentation. Thank you.
Yeah, thank you so much for the introduction. And it's really good to see so many of you here. As Lisa Marie has said, I'm giving this presentation together with my good colleague, Flora Cordoleani. But if you go to the next slide, you can see there's a big research team, of course, behind this project. Carson Jeffries at UC Davis is one of the other PIs. We have Eric Pelkovics and Pedro Valencia Landa at UC Santa Cruz, Rachel Johnson at NOAA, Yelma Erkens and Jeff Rosenthal are our archaeological specialists on this project. And then George Whitman, who's been instrumental in getting all these samples prepared and analyzed. And then our funding sources, of course, the main funding source being the Delta Stewardship Council, as well as the U.S. Bureau of Reclamation. And then we had watershed-specific funding, one from NOAA Fisheries Office of Habitat Conservation for the Yuba River, and also from U.S. Fish and Wildlife for Battle Creek. And then all of the work involving archaeological samples was carried out in collaboration with Estom Yumika Maidu tribe of Enterprise Rancheria. So if you go to the next slide, our project had multiple objectives. And to summarize this really quickly, we were looking at the life history diversity of spring run Chinook salmon in the Central Valley, both across space, so among different watersheds, and then also through time utilizing archaeologic samples. And the idea was to really look into the details of what these fish are doing in different watersheds and at different climate conditions, and learn something about their life history diversity that hopefully can inform our management and conservation. And so if you go to the next slide, just a little bit of background. I saw the name of the attendees here. I think most of you are way more familiar with Chinook salmon than I am. In California, we're at the southern end of the range, so they're experiencing a lot of stressors, both in the freshwater phase, but then also in the ocean. They're migratory fish, and they really depend on a lot of the different, they really depend on freshwater and estuarine conditions in the Central Valley. There's this good report by Moyle et al. 2017 looking at that they're really in trouble under the predicted climate conditions. And so go to the next slide, I think. Yeah, one of the main stressors Chinook salmon experience in the Central Valley is, of course, that we have disconnected them from the habitat. So in blue, you can see all the rivers that Chinook salmon used to be able to have access to, really diverse mosaic of different habitats. And then as we go forward to the next slide, you can see all the areas in black now that we've lost through dams, water diversions, many, many other processes as well. Next slide, you will see, maybe unsurprisingly, populations of Chinook salmon in California have been reduced. Winter run now only exists below 1 dam. Spring run are really struggling, and then fall run are heavily supported by hatcheries, but even they are struggling as well. And the fishery is again closed this year. So we're going through these boom bust cycles of Chinook salmon abundance. And one of the factors that may be driving this is that they've lost a lot of their life history, diversity, to be able to deal with all these different environmental conditions, both in freshwater and in the ocean. Next slide. Okay, so we wanted to approach this really complicated topic and use one of the chief tools that I've been using over the last years, which is looking at otoliths or fish earstones. They're really an amazing archive that we can collect. They contain individual information on each fish throughout their entire life. We can look at the macro and microstructures and learn something about how old that fish is and how it was growing. And we can do geochemical analysis as well. And then basically reconstruct the movement of that fish through different freshwater and estuarine environments and into the ocean. Next slide, you will see some of the life history metrics that we considered in this project. We were interested in age, size, return type, natal origins, habitat-specific growth rates. And then one of the key factors that we're going to highlight here is the outmigration timing and size from the juvenile phase. So if you go to the next slide, I think I'll let Flora take over from here.
Right, thank you, Malte. So like Malte said, we were interested in looking at the outmigration timing and the size of the juvenile fish when they leave their natal tributary. And we were considering several tributaries from the Central Valley. Specifically, we looked at Mill and Deer Creek, Butte Creek, the Yuba River, the Feather River, and Battle Creek populations. Next slide, please. So first of all, we had some data from Mill and Deer Creek springland population, which is one of the stronghold of springland salmon stock in the Central Valley. And we were looking at the Rorty screw trap data. So those screw traps are put in the tributaries during the juvenile outmigration season to catch juvenile and determine when they are leaving the system and at what size. And on the graph here that you see on the left, you can see that there are 3 main life history strategies that are found across within this population. And the most common one, or the most abundant one, was the fry strategy, where fish leave the natal tributary at small size a few weeks after they emerge from the gravel. We also saw some smolt fish, where fish spend a few months in the tributary before leaving to the ocean. And then there is also a large yearling component in Mill and Deer Creek population, which is when juvenile over summer in the natal tributary before leaving to the ocean in the following summer, fall. Next, please. Now, when we looked at the strontium profile that we got from the returning adult otoliths, we were wondering, are we going to see the same proportion and the same life history strategy? So which one are actually successfully supported through the life cycle and through the adult that come back to spawn? And what we can see is actually we see the 3 strategies, but we see a large amount of yearling. So what was really interesting in this population is that the yearling component was very instrumental in the cohort support. And especially, next slide, please. We found that a lot of the during outmigration years that were warm in 2015, 16, 11, 12, and then 9 and 10, the late outmigration strategy, which corresponds to the yearling, was the dominant one. So really the yearling migrants were dominating during drought conditions and were saving the cohorts during those years. So that was what we found for Mill and Deer Creek population. And so based on that, we were wondering if it was the case, if we were going to see the same thing for the other spring run population. Next slide, please. So we looked at Butte Creek, which is currently the most abundant spring run, wild spring run population in the Central Valley. Next slide, please. And again, if we look at the rotary screw trap data, we see the three migratory strategies: fry, smolt, and yearling, with fry being the most abundant proportion of fish caught in the rotary screw trap. Next slide, please. And then when we look at the Downstream isotope profiles, what we saw actually is the majority of the fish were out migrating from the Butte Creek watershed at smolt size. So they were spending most of their juvenile rearing phase in the freshwater, in the Butte Creek watershed, before migrating to the ocean in the spring. Next slide, please. And several other studies that we've been doing in the Butte Creek watershed leads towards the thought that they have access to what we call a floodplain habitat, which is comprised of the Butte Sink and the Soda Bypass. And we've seen that there is high growth opportunity there. You can see on this picture on the top right from Jeremy Notch, a large juvenile Chinook salmon from Butte Creek. So we think that those fish actually spend a good amount of time in those off-channel habitats and grow as large, small size, and they leave the tributary after that. And so you can see a question mark in the rotary screw trap data because there are some of those fish that were categorized as yearling based on their size at date. But we think that they might actually be just very large smolt that are actually just seen in Butte Creek watershed because they have access to this amazing floodplain. So the strategy found in Butte Creek population was very different, or the strategy proportion and the overall life history diversity was very different compared to Mill and Deer Creek. And it makes sense because of the elevation and the access to different habitats in this watershed compared to Mill and Deer Creek. So then we went to another tributary where spring run was found. And next slide, please. So we wanted to highlight what we found in the Yuba River. Next slide, please. So again, if we look at rotary screw trap data, we have a large amount of fry leaving the system. We also find some smolt, but very few yearling are actually caught in this river. Next slide, please. And when we look at the returning adult Downstream profile, we actually find that the majority of the fish migrate out of the Yuba River as fry. There are also some smolt, and very, very few yearling. Next slide, please. And that's shown here in this slide again on the left. And if we plot the proportion of each life history strategy by year that were analyzed, we can see that the early migrants dominate in all years. And they are even more in larger quantity during warm out-migration conditions in those 2 years in the right. So surprisingly to us, it seemed like fish juvenile in the Yuba River tend to not spend too much time there and migrate to downstream habitats and find some good rearing habitats as fry in maybe the lower Sacramento River or the Delta to grow before they migrate to the ocean. Thank you. Another metric we looked at with the otoliths is the natal origin of those fish. So trying to confirm that the fish that were caught during carcass survey were actually coming from that tributary. So were born there and came back to this tributary. And so we're showing you here the predicted natal origin for 4 of the tributaries that we studied: Battle Creek, Butte Creek, Feather River, and Yuba River. And what we can see is, first of all, for the Feather and the Yuba River and Battle Creek, there is a large hatchery fish influence in the samples that we were studying. And especially so for the Feather and Yuba River, this is a lot of fish from the Feather River hatchery, which is not surprising. And for Battle Creek, there is a large influence of Coleman foreign hatchery fish. But we also found some native origin population in the Yuba River, which was a great confirmation that there is a sustainable springland population in the Yuba outside of just Feather River fish. Butte Creek was mostly native fish. There was not a lot of stray. And then what we saw as well is in Battle Creek and the Feather River, there was an important wild stray influence. So wild fish from other tributaries coming to spawn in those two watersheds. Next slide, please. And then I will let Malte take over again.
Okay, so that was a really quick overview of one of the life history metrics across different tributaries to the Sacramento River. One unique component of this research project was that we also wanted to look into the time. And we know that's really important because along the Pacific Northwest, we have lost a lot of our salmon population since European contact. And so we may have lost a lot of populations already in California. We're collecting data really on a remnant data set. And so endogenous records, or like archaeological remains and traditional ecological knowledge may be really useful if we really want to understand what these fish used to do and what they are potentially able to do. And so go to the next slide. We were in the unique position on the Feather River to have 18 archaeological sites where salmon bones were found in a really small stretch. They're all in the lower Feather River, so above Yuba City, but below Oroville. And they range in dates between the mid-1800s to about 6,000 years before present. So they cover a huge range of different environmental conditions, both times in the mid-1800s when the climate was much wetter in California, but then also further back in time where we had extensive droughts. So go to the next slide. Oh yeah, so one thing, of course, to remember is that if we're working with archaeological remains, that these are really highly biased samples. So someone went out, caught a fish, brought it back to the village, prepared it, cooked it, ate it, and 6,000 years later, we find those fish remains and analyze them, right? That's very different than our well-stratified surveys that we're doing now. By definition, these samples are biased. And so that's something we need to keep in mind when we try and get information out of this. We should be a little bit careful, but I think there's still a lot of useful things that we can learn from this data set. And I want to spend the last couple of minutes highlighting some of our findings here. So go to the next slide. So one of the things we were really interested in was the return age of salmon. We know that in our current spring run population, most fish are 3-year-olds. A lot of hatchery fish are actually 2-year-olds. And then in this plot, you can see as we're going back through time, so say to the mid-1800s, but even further back in time, it seems like 4-year-old fish are really, really important and are really common in our archaeological site. And in the mid-1800s, we even find a lot of 5-year-old and even a few 6-year-old Chinook salmon, which we are really not finding at all anymore on the landscape. So we've lost a lot of this age diversity over time. And there may be some relationships here to different climate periods. We looked at this really, really broad scale. You can see during the wetter period in the mid-1800s, maybe there is some older fish available returning than during the drier periods that just preceded it. But that's a really coarse first look at these data. Go to the next slide. We can also look at the same juvenile outmigration life history metrics that Flora just looked at, summarizing the modern data here on the left graph again for the different watersheds. In red, the fry, in green, smolt, and in yellow, the yearling. You can see how different Mill and Deer Creek is there on the left. And then if we look at the Feather River on the right, we can see that really through time, there's very little change. I should have highlighted here the mid-Holocene period, like that last time point there, the 5,000 to 6,000. That's 2 samples. So really looking at proportions here isn't that useful, but we have never really looked at 5,000 to 6,000-year-old salmon before, so I didn't want to remove those data points. But it doesn't really look like, for example, either a high fry component or either a high yielding component was very common on the Feather River, at least not in our samples. But there's one really interesting exception to this. So if you go to the next slide, there's one archaeological site that dates to the 1800 to 1860s, which is a time when the Central Valley was repeatedly flooded. You may know that famous painting of Sacramento underwater. I think the capital had to be relocated to San Francisco for a number of months. Massive floods events were occurring year after year here. This is before levees were built. And so if you go to the next slide, we really wanted to look at, again, one of the life history metrics, but this time we wanted to look at what fish were doing during their adult time. So what were fish doing after they left their freshwater natal river? This is an example of modern spring run. Each bar represents a fish. You can see there's 2-year-olds, 3-year-olds, and 4-year-olds. We've all normalized them. That's why the bars all look the same height. Green is freshwater, like the light blue is the estuary, and then dark blue is the ocean. So modern spring runs spend very little time in freshwater and the estuary, go to the ocean for most of their life and then return. But then if you go to the next slide, you can see some of the samples we analyzed here spent extended amounts of time in the estuary. So this is one site on the Feather River that really shows us a life history strategy that we're not observing at all anymore in our modern spring run population, that we're not seeing very much either in our archaeologic samples, but it is something unique that was happening. Thanks. I was trying to click to the next slide and realized I couldn't. So that's really surprising, right? To see this different life history strategy. Maybe it's not so surprising if we think about how different the system is now than it used to be, even in the early 1800s, even after European contact. We've lost a lot of our delta habitat. We've lost a lot of habitat in the estuary. Last week, we heard a really excellent talk about all the habitat we've lost in Suisun Marsh, for example. So there used to be a lot of low salinity freshwater habitat available for salmon that's not available anymore. And there seems to be a life history strategy of salmon that used to be taking advantage of this habitat. Again, these are archaeological samples, highly biased. We're not at all saying that most fish at that time did that, or even many, but it seems to be a strategy that was used by some fish. Go to the next slide. I know we're running a little bit long, but I don't want to rush through these. So we have only 2 more slides to go here. So some key take-home points from our research so far is that Otolist can be really useful to look at these life history metrics, and it's really hard to get these data any other way. Applying these tools, we've seen that Chinook salmon in California, specifically spring hung, have lots and lots of different life history strategies that they use, and even in really close proximity. So even some of these rivers, right, on the scale of Chinook salmon range, those are really close together, but those fish really do very different things. And then these archaeological samples can really give us interesting snapshots into the long-term baseline and show us what these fish used to do. And that's really important. I really like these 2 quotes. One being that we're really losing this interspecific variation at a rapid pace, and we are not noticing it. We're focusing on abundance. And often we are losing this variation, and then our stocks collapse. And then the famous quote from Hilborn that we really don't know which of these populations, for example, of spring run, is going to be really important in California in the next 10, 20, 30 years. Is Butte Creek going to be the most abundant one, or is one of the other rivers going to become more important? And if you go to the next slide. So some of our recommendations, of course, is we should really be managing for diverse spring run Chinook salmon, for a diverse salmon population. So rather than just focusing on abundance, And on the flip side, that means if you're doing a restoration project or anything like that, and you don't see the salmon abundance immediately increase, like maybe you're increasing the resilience of the stock nevertheless. And we should be monitoring for that. And connected to that, of course, is that these diverse habitats do a lot better if they're all connected. We need to provide access to these habitats for salmon as many time points as we can. So we need cold water pools, floodplain, off-channel habitats. We want all of this. And then if we think about the Yuba River and the fry leaving, they're rearing somewhere before they go to the ocean. So these non-natal rearing habitats might be really, really important. Next slide. I was lying, there was a third slide. Okay, so next steps, we're really interested in further quantifying interspecific diversity using our Otolith tools to look at phenotypes, but combining that with genetics. Otolith and genetics go really well together to look at genotypes. We want to incorporate islands research, so look at not just where the fish are, but also what they're eating and how that relates to growth. And then, of course, further explore those archaeological collections. I think we're really only scratching the surface, what we can learn there. We haven't even really touched looking into traditional ecological knowledge here. And with that, I think there's one last slide that just has our emails, but yeah, we're done. I'm happy to take any questions. And sorry for running long.
There is no need to feel sorry. That was absolutely fantastic and just amazingly resourceful. I don't see any questions in the Q&A, but I do think there might be some in the chat, so we'll have to see. I've already heard a couple. This is fantastic talk. Thank you, Flora and Malte. Eva, do you want to ask your question directly?
Sure. I just love this project. It's been really fascinating to learn with, and I've definitely have developed a huge appreciation for salmon just from working with y'all. I was really fascinated by the photos that you had of the excavation site. So I was wondering, was the excavation at Feather River exclusively for the salmon bones? And if the excavators needed special training to find such small remains? I find that would probably be kind of difficult to spot.
No, that's a really good question. So no, they were the salmon bones were a byproduct. The excavations, if I understand correctly, they happened long before we started this project, or long before, like in the mid 2010s. They were all part of the levee. There was levee work being carried out to repair the flood protection structures along the Feather River. And as part of those projects, these archaeological sites were partially excavated together with the tribe. And in those excavations, all kinds of animal and plant remains were identified, and some of these villages were reconstructed. There's a number of reports that are coming out now detailing these different archaeological sites. And you're absolutely right. Normally, fish bones are not the key focus of archaeological sites. The otoliths specifically are so tiny that they're often not identified. And then even archaeologists who work on bones normally disregards the otoliths because they don't feel like a bone. If you pick them out of the dirt, they actually feel like a little piece of rock. And so it's only really recently that people have started looking into otoliths in more detail. And I bet there's all kinds of samples available in some archives in California that we don't even know about yet.
Thank you. Let's go to the next one. Let's go with this one from Denise Colombano that just came in. Just put it in there. So she says, thank you, Flora and Malte. The archaeological study showing the historic use of the estuary, light blue bars, is fascinating. When you suggested that the decline in modern salmon populations may be related to the lost life history strategy of estuarine rearing, you showed Alison Whipple's SFEI plot of historic delta landscapes. But then your key takeaway is that habitat mosaics, such as floodplains and off channels, are important to promoting life history diversity. Why not tidal marshes?
Oh, I think absolutely also tidal marshes. Sorry. Yes, I think all the habitats. I think you're absolutely right. And I think a project that would really detail specifically the mid-1800s and all the habitats that we've lost in the San Francisco estuary, in the Delta, but also all along the river corridors, right? Like along the Feather River and all the tributaries of the Sacramento. That would be really fascinating. One of the problems we've run into with this project, this is really, it's really hard to imagine if we're standing in the Central Valley now that the salmon could hang out for like 2 or 3 years. And even looking at these maps, even I'm looking at these maps, I'm still like, hey, can this actually work? And then once you realize all the habitat we've lost, you're like, okay, yeah, maybe.
So yeah, on that, oh, go ahead. Oh, sorry.
Can I add just, to me, tidal marshes completely, they are kind of included when I say off-channel habitats. Anything that is not in the main river is kind of a great off-channel habitat. The difficulty we had is sometimes to distinguish the strontium signature from those little intermediate habitats compared to the main stem. So it might be harder to find a difference in strontium values in some of those tidal marshes compared to the main delta, for instance. So we would categorize that as a delta, for instance, but it could be that is not in the main stem of the Sacramento River or the San Joaquin River, but it would be in some of those marshes. What is great with the floodplain is that they are large enough and they have a signature that is specific enough that we can separate them from the main stem rivers. But yes, I agree. All those off-channel habitats are probably very important for Chinook salmon. And like Malte said, that might be very important for the Yuba River fish, which are rearing somewhere not in the Yuba River. And we don't know that yet where. And the islands could help us with that as well, because we can do isotope analysis on those as well. And the sulfur signature can tell us a little bit more on where those fish were actually feeding, and where is the food web coming from.
Thank you. Can we stay on this theme for a second and talk about operationalizing the idea of mosaics and the importance of variability in habitats and such? Do you have any recommendations about how restoration managers can make the case, and how much restoration variability would it take to see these mosaic benefits? And maybe even if you could get to how much effort should be put into restoring floodplains versus other habitats, cold water refuges and such.
Do you want to go? Or I
Oh,
think,
your floor.
yeah, I think, yeah, my just as a scientist, I would think in terms of like having infinite amount of money and not really like having to decide on where to put restoration or not. And to me, they're all important. So like we show Mill and Deer Creek, they rely on cold water pool for their yearling component. So if you have some cold water habitat that could be available for a tributary, then I would work on getting the fish accessing those cold water pools. But then at the same time, if there's also some off-channel habitats that were existing or could be created, I would also try to do that. What we wanted to highlight is that it's not only in a little tributary that this is important, but you also want to have that in downstream habitats, because a lot of those fish just get out of the natal reach really quickly, so they need to find some rearing habitat downstream. So I would do it all, which is probably really hard.
And
yeah.
if I can add to that, I think what could be really interesting first step in that direction would be to have more collaboration among the different rivers. Like each river, at least to me, feels like it's really working a little bit independently. And of course, all these populations are somewhat connected. And so I don't know what that would look like, if that's like future workshops or someone, because I feel like I don't feel qualified at all to say where we should be putting the effort in terms of restoration. But I know there's a lot of people on the ground actually doing this work who probably have really, really good ideas. One example would be on the Yuba River, where I think most people working on spring run wouldn't even consider that important, but one of the main spring run populations. But then we're finding there's actually quite a number of spring run fish there. They just leave really early. So yeah, I think getting people who are working on these rivers all into one room, and I think your question is excellent. I don't think I can answer it though.
As long as we're talking, then we're making progress. So it's good to hear. Yeah, there's just keeping on the idea of all those different rivers. I'm wondering if you could speak a little bit about the involvement of the Maidu tribe regarding the importance of Chinook, or to be more broadly, just how different groups of people relate to and value Chinook salmon amongst these systems that you studied.
Yeah, that's a really good point. So the chief involvement of the Maidu in this project was really on the excavations. And then they are, of course, really interested in talking with us about Chinook salmon and what we're finding. I think compared to maybe some of the other tribes in the Pacific Northwest, the inland tribes in California are more disconnected from salmon. I feel like if you're in the Feather River, you're really far away. You're really far away from salmon. And I feel like we are, as scientists, are really disconnected. I didn't know, for example, that there are a lot of like salmon festivals still happening on the Feather River. And so we've been working with the Maidu on this specific project. And I'm really hoping that some of the like bits and pieces of information that we're finding are a good way to start this conversation and learn a little bit more about this. This is also that these excavations, like how these samples are collected, is a little bit tricky, and I think that's something in the future we can also move forward. And when this repair work is being done on some of the levees, involving tribes really early in this process and making sure that, for example, we look for salmon bones, we ask them which fish species they're interested in. And in our project, we focused only on salmon, but there are a lot of other fish bone and a lot of other animal bones in these sites. It could be really interesting to study. So yeah, I think we're really only scratching the surface, and building these collaborations is going to take a little bit of time and trust.
I couldn't unmute for some reason, but that was a great answer. Actually, I think we just have to build trust and keep working in that direction. This is just such an incredible study. There's one question that came in. I'm going to feed that one out. It's from Miranda Tilcock, and it's it gets into a pretty direct question to one of your graphs. She says, "How come we don't see any hatchery strays in Butte when there were so many in the other locations sampled?"
It's a good question, Miranda. I asked CDFW about that, and that's historically they haven't seen a lot of stray or hatchery fish in Butte Creek. Maybe because they are a little bit further from the hatcheries compared to the Yuba or Battle, which is directly in contact with the hatchery. We haven't done the natal origin modeling for Mill-and-Deer Creek fish, but I'm pretty sure it would be the same thing in Butte Creek. They have less straying from hatchery in their tributary as well. So I'm not sure if it's because the water is where their signature is very different there. So and then we're a little bit further from the hatchery, so like the hatchery fish just tend to not go that far outside of their range, or if there is something about the tributary by itself, the watershed, that makes it that they don't really go all the way to the spawning ground. It is pretty high up for both Butte and Mill-and-Deer, so not sure.
Well, further research then, or future project. Thank you both so much. Is there any last thoughts you wanted to make before we switch to the next presentation?
No, thanks for having us. And if you have any more questions, post them in the chat or send us an email. And always happy to discuss. Bring on.
Yes, and just didn't really talk about it, but I mean, it was highlighted in the slides, but there are 2 papers that are coming out. We have a lot of papers coming out from this project. There would be more to come. Right now, it's about the Yuba River. There's going to be a lot of paper out for the Yuba, which is great. But we have some work published from Melandier and Butte Creek, and we're working more on analyzing. We still have a lot of work to do and more to come. So just keep an eye open. This project is full of interesting information and data.
Thank you, Malte and Flora. Okay, let's move to our second talk in the series. I want to highlight that again, it's another one funded by the U.S. Bureau of Reclamation. I was glad that Malte and Flora highlighted all their funding sources. And this one also with your Bureau of Rec funding, it is also focused on the same science action agenda topics that of the previous project, which is capitalizing on existing data through increasing science synthesis, as you heard, improving understandings of interactions between managed species, stressors, and communities, and then also modernizing monitoring, data management, and modeling. So this talk is by Alexander Forrest from UC Davis, and he's going to be presenting on regulation of controls of cold water through the temperature control device of the Shasta Dam as a means of supporting downstream fish populations. So we have Alexander, we will move forward. Thank you.
All right, perfect. Can everybody hear me? Yes.
Yes, we can hear you. Thanks.
Perfect. So good morning, everybody, and thank you to the previous presenters. I have all kinds of questions coming out of it because this project is definitely as far away from the Delta as you can get. So this is looking down the spillway of the Shasta Dam, where a lot of the temperature control, and we talk about quality of water and quantity of water. So how much water is coming down the Sacramento River and what's the temperature of that? So I am an associate professor in civil and environmental engineering at UC Davis, but I also am part of the team at the Tahoe Environmental Research Center up in Lake Tahoe. And so we have quite a diverse team of folks working on this. We're also partnered with some private consultancies on this project for modeling temperatures downstream and how that impacts fish. And then finally, Andrew Ripple, who is also working on the downstream component. I'm going to be presenting on a lot of the work we're doing right at the headwaters today, up in the dam itself. So the Central Valley Project, for the many people know, so 20% of the total water supply to California is provided by the Central Valley Project. And so this really controls the quantity of water and how it's moved around. Now, the Shasta Dam and Reservoir, created in 1945, is at the very northern end of the state, up near Redding, and it controls about 41% of the volume that flows through the Delta. So an incredible amount of water is flowing through this dam. When it was initially created, it was actually created for flood control initially. And what they noticed was that the downstream temperatures weren't being regulated very well, and it was getting very warm. And so they created in 1997 the TCD, the temperature control device. And I'll walk through what this is and how they use it to regulate water temperature downstream. Now, this is really critical for cold pool management and the timing of that water and as it comes downstream, particularly for winter run Chinook. And there are papers out looking specifically at that. Next, please. So tying to this, the agenda, so the science action agenda connections, we're really trying to capitalize on existing data, so partnering with the Bureau of Reclamation and others to try to synthesize various data sets, and we'll be talking about that, and then also collecting new data to place the old historic data into a framework of understanding. Then to also improve understandings of interactions between the stressors, managed species and communities, well, basically, nobody worries about water when we have plenty of it and it's the right temperature. But that's rarely the case in California. We're either in flood or drought, and we have to be able to adjust continuously to maximize the protection of species downstream. And then finally, because I am an engineer and bridge between science and engineering, I'm always, myself and my team are working on developing new tools to help modernize the tools we're using to make decisions both upstream and downstream. Next slide. All right, so looking at what the TCD is, so the temperature control device. So if you look here at this schematic on the right-hand side, you have the crosscut of the Shasta Dam with water flowing through to the powerhouse. So this water, that connection never changed. Now, what they did in the mid-90s is create this structure that essentially lowered down and bolted to the side of the dam. And then there's a series of gates that are controlled with louvers. So think basically Venetian blinds on a window that they can open and close these gates to let water in to go through the powerhouse. Now, during the summer, we get peak flows of about 15,000 CFS of water that they're releasing, and they're able to draw it off through various points as the water heats up during the summer, and then gradually the thermocline, or that layer between the upper water that's warmer and the lower water that's colder, sort of migrates down through the season. So they can sort of chase the cold water through these gates. And to give you an idea of scale, the TCD itself is about 400 feet tall. And so it's quite a large structure. And there are issues with its operations. Just leave it at that for the moment. So how we initially got engaged with this is trying to understand the dynamics and the water velocities around the TCD to then improve the understanding of in-reservoir and dam release water temperatures. So this was a structure that was created in the mid-90s. The structure itself, they do ongoing maintenance and repair, but it's an aging infrastructure. And so they know they are getting leakage and between different gates during different operations. And so they're trying to quantify this in order to maximize performance downstream. And so as part of this, it's also trying to understand what we call the withdrawal zones. So basically, if you open a gate, it's not just a straight drawing through of the water. Instead, what it does is sort of makes an envelope that we get that draws from both upper waters and lower waters. And so trying to understand what that envelope looks like is something that's very important. And so this is because some of the questions we're starting to ask is typical operations are to open all gates at a given layer. So there are 5 towers, and you'll see more schematics of these as we go along. There are 5 towers across the TCD, and then these 3 sets of gates. So typically what they'll do, say for example at the upper gates, is they'll open all 5 towers at once and then let it run for a couple months like that. And then as it's on demand with the turbines in the powerhouse. And so then some of the questions are becoming, can we open different sets of gates to maximize the performance? And for both short-term conditions, so sub-daily, and then long-term seasonal conditions, to really try to get every bit of cold water that we can. And then finally, to quantify the leakage under different storage and TCD operations. So we spend a lot of time focused on what steady state conditions are, but what about unsteady state conditions when they're opening and closing or ramping different turbines up and down in the powerhouse? Next slide, please. Oh, next slide. Thank you. Okay. So here is sort of a more three-dimensional view of the gates and of the TCD. So we have the upper, middle, and lower gates. We also have the side gates, which are really their last-ditch effort to draw cold water in from as low as they can in the reservoir. That's still not right at the bottom, so there is usually a little cold pool left over there. And generally, they'll only draw from the side gates every 2 to 4 years. But this is a complicated system, partly because what we're showing here in front of the gates is the actual bathymetry. And so what happened is when they were building the original structure, the original dam, that flat plateau in the bathymetry is actually the original site where they had the concrete tower delivering concrete into the dam itself. But what they created was kind of a little rise where the water flows down the original riverbed of the Sacramento River and then turns into the gates. So trying to understand what that looks like is something that's, it becomes a much more complicated problem than just drawing water straight in. I said the entire structure was several hundred feet tall. Individual gate levels I have listed here. So the middle gates are the thinnest at 28 feet or approximately 30 feet. The other ones are 45 and 50 feet wide and 45 feet tall. And all of them are 50 feet wide in each of the towers. So I then spoke about stratification. So basically chasing the thermocline as we go down. Now, TCD leakage, it has been a known thing for years, but the magnitude of this leakage is poorly quantified. And so that's something that we really need to get our hands on. Next slide, please. Okay, so we have had a series of tests and we have ongoing work this season that I'll talk about at the end. But to do the preliminary work of this, we went in 2021, which is one of the extreme low water years where we knew we were going to be getting side water withdrawal. 2016 is an example when there was a lot of fish kill-off. 2021 was as well, where they're trying to just preserve as much cold water as possible. The panel on the top shows the flow rates. So you can get peak flow rates at about 18,000 CFS, but more typical day-to-day operations vary between 8 to 14,000. And then, so you can see here as we're moving through, they never even used the upper gates during this season because the water level never was high enough to be there. So they started in the middle and then transitioned to the lower very quickly. They did a blend for a while to see if that would help with cold water management. And then they went right to side in August through December to try to draw as much cold water as possible. So we went in July, right at the end of July, and tried to monitor during high and low flows. This was during a strong stratification. And when I say high and low flows, is because we were there, they ramp up and down during the day, depending on what the electrical demand is into the grid downstream. So timing this, we could be out there at 10 a.m. With a flow rate of maybe 1,000 or 2,000 CFS. And then by 4 p.m., they'll have ramped right up to 15,000. So they're really creating a system that draws and surges water downstream. The equipment that we used was a vessel-mounted ADCP, which is an acoustic Doppler current profiler, and a lowered ADCP, as well as a CTD profiler. So this measures conductivity, temperature, and depth to allow us to characterize what the water column looked like, both in terms of water quality with the CTD, as well as the water velocities and how the water velocities are moving. Next slide, please. Oh, sorry. So these were our 2 time periods. And try next. So what an ADCP is, so this is actually not in Lake Shasta. This is in Lake Tahoe, which is much clearer and easier to see our moorings. But this is very typical of what a mooring looks like for us, where we have a sensor on a string suspended in the water. It then transmits out acoustic signals, and then it measures the Doppler shift to record the water velocity within a certain range of the instrument head itself. Now, depending on the frequency of transmission and the frequency of the instrument, this will limit the range and resolution. And so this is one of the big challenges with working in this environment, is that we are trying to work very close to a wall. So we're getting side lobe reflections with the acoustics to try to measure what those acoustics are. We're trying to work in an area where it's quite deep. It's about 600 feet total in depth. And so we actually have to lower this instrument in to whichever place we want it to be. And then there's also a lot of, let's call it acoustic reflectance debris around. So there's a lot of metal work that's left over from the original construction. So when they actually built that concrete tower that I initially referenced, they actually just cut off the top of the tower. And so the superstructure of the tower still sits on the bottom of the lake, and it actually gets exposed in drought years. And you can see, but that metal causes reflectance of the signal. So actually from an operational point of view, this is one of the more challenging places to work with these instruments. Next slide, please. So these plots, if you can, for a second, were produced by one of my students who did a great job trying to process all this data and try to understand this data and process out all these acoustic reflectance and challenges that I was talking about. And so here, what you're looking at is a top-down view looking into where blue represents flow into the dam. And so we have high and low flows in the first 2 panels in July. So you can see the complexity of the withdrawal envelope and where that water is being withdrawn from. So here during the July high flow, it's actually pulling water from near the shoreline into the system, rather than drawing that water up from where that colder pool is off to the left. And then during low flows, you actually see a little bit of potential residual return flow. And this is something that we're trying to understand exactly what that dynamic is. And then November, we also have flow flowing in. Next slide. And then these 2 sets of plots show the front and side views. So here in the first 2 sets, we have the flows coming in at the lower gates, as was expected. So in panels A and B, it was all expected to be coming in at the lower flows or lower gates. And what we weren't expecting, so if you look at the second set of panel on the right, panel B, is the non-uniformity of it, that dominantly they're coming in through towers 1, 2, and 3, rather than the other 2 towers. And so that's what we're trying to understand now. However, what was more interesting for us was what was happening in November. So remember, in November, we had water being withdrawn from the side gates. So that's the water at around, that's the gates here at around 720 feet. This is where we're expecting the water to be coming in, and it's supposed to be colder to help protect the downstream populations. What we're actually seeing, though, is water coming in here through the lower gates. So we're actually seeing more water intruding from the side. So this has a lot of implications for how we're managing the water and how we're managing the water that will ultimately flow downstream. Next slide, please. So that November, yeah, if you don't mind going back, it's just highlighting the leakage in November. So this is really the one that we're trying to understand during these critical conditions. Next. So to not get too thick into this or into the weeds, we can spend time. There is theory looking at the withdrawal envelope that will form. This is assuming that the water is unstratified. So when you stratify your water, this envelope gets thinner. So for a typical open gate height of approximately 45 feet, you're looking at a withdrawal envelope of nearly 175 feet downstream that will eventually asymptote to. So this is in relative agreement with what we were seeing. And so we have to factor that in to understanding where we're drawing the water from. Next slide. So leakage rates. So this is a view, if you can imagine, here is imagine this is the water line, right where the cursor is. You're looking above the water. This is the actual structure of the TCD if you're sitting in a boat on the water. Then underneath that, you have the gates that sit submerged. And so here are your upper gates, and then you have your lower, then you have your middle gates here and your lower gates down here. And we know that there's leakage. There have been efforts before in the past with divers and ROVs to do work on the middle gates during lower flow conditions. But it's very challenging because they can't shut down operations. So we were working specifically trying to prove this concept of using acoustic products and acoustic tools to be able to characterize these environments and also to see potential damage of the louvers themselves. So in the summer, leakage is not as evident, but in the fall, leakage is. And actually made up a major fraction of the flowing downstream into the powerhouse. And this is also evident in the model versus measured downstream temperatures. So if you model using a blend in the model, you can better approximate what we're seeing downstream. And when I say blend, I mean, if you sort of factor in a 10 to 20% leakage rate from one set of gates versus another, that gets us closer to the true value of the temperature. So in order to get further there, we really need to do a better job modeling that. And really understanding what those leakage rates are under different conditions is where we need to get to. Next slide, please. I think there's one slide missing. Go next slide, please. Okay. Yes. Okay. Back one slide. I'm not sure how that happened. I'm putting my apologies. Okay. So during this season, so in April 2024, temperature and velocity moorings were installed to monitor the seasonal changes for summer and fall stratification. So everything that I've presented for 2021, really we were focused on the spatial distribution, trying to characterize these envelopes, but they're snapshots in time. And so what we're trying to do now is trying to understand how it varies for the entire season, which is the ultimate goal of the work through the project funded through the Delta Science Council. So we installed one mooring in front of Tower 3, maybe slightly to Tower 4, 75 feet from the intake. This is one of the more difficult moorings our team has been involved with in a while. And so that got installed in April and will be there through until the rains start in the fall. And then we also installed a high-resolution temperature mooring about 500 feet away from there in the deepest region of the lake. This ball float that you see on the right is the surface expression of our mooring, and it's monitoring the temperature, so we can combine this idea of temperature and velocity together. And then because we're trying to resolve the temporal changes, and at the same time, we have a number of trips planned. We have 3 trips planned during the summer, during each of their operational changes from each of the major gates to resolve the spatial changes in the withdrawal envelope. Next slide. This should work. So, in conclusion, we have multiple demands for environmental flows. So we have demands for electricity, for flood protection, for environmental flows, for fish protection. And so to do that, we need to continue doing a better job of modeling. And to get there, we need to quantify gate inflow to the TCD to improve the model representation that supports temperature management and reservoir operations. And integral to that is quantifying the leakage for the temperature management. I mean, there's an expression that I'm sure many people have heard in California that whiskey is for drinking and water is for fighting. And that's particularly true during low water years. And I have this return period here showing the return period of the minimum annual elevation in Lake Shasta. And we are seeing increasing number of low water years. Even though we've had high water years over the last decade, you can actually look back over the last decade and see a number of very low years, like 2015, 2016, that was a terrible year for fish, 2021, which was a very bad one. And so this is a really important thing in terms of water quantity, but then I always talk about water quality as well. So an interesting thing from this year is that they will be going to side operations, even though they have a lot of water this year and all the reservoirs are full. The water qualities came in quite warm because we got a lot of that water right at the end of the season. And so a lot of that water flowed in a lot warmer than usual. So they know they're going to be going to side water operations much earlier than they expected. So the question of water quantity is one and water quality is another. And now if you can go back 2 slides for my final thing, I just wanted to acknowledge the Bureau of Reclamation, the Delta Science Council, and the Sacramento River settlement contractors who have been supporting our work at Shasta Dam for the last number of years. So I think I'm sort of on time.
You are. Thank you so much. I have questions, but I think I'm going to go straight to the Q&A that's been posted so far. It's just such a huge operation, that temperature control device. I just got a tour of it in May, and it's great to see this kind of detailed assessment of its effectiveness. The first question we're going to take is from Dylan Chappell. It's great talk. Thanks, Alex. What are the implications of water year type for your findings? And I'm thinking about that last slide, maybe even that you just showed in your conclusions. What are the limitations and benefits of the data you've been able to collect over the project term, and what would be beneficial of data collection in other water year types?
Okay, what are the limitations and benefits?
Yeah.
Well, let me start with limitations. It is a very, very challenging environment to try to operate in. And we want to inform decision-making in terms of operations, where basically we have an infrastructure that will be very hard to change. I know there is discussions happening at a very high level of, are there ways to retrofit the temperature control device in the future? that the price tag for that is going to be enormous. And the price tag will be enormous, and the design will take a long time. So in order to continue with what we have for, let's say, the next 5 to 10 years, we really have to know how the thing is operating and how, if it continues to fail. So we need to continue monitoring this. So ideally, what we would do is actually install equipment directly on the temperature control device itself. However, doing that is extremely challenging. So we're trying to do it in almost a remote sensing capacity, but it's extremely hard to do that. So we're trying to sort of balance the quality of data that we can get with the complexity of the system that we can get to. And so, however, those are some of the limitations, but the benefits are we can inform decision-making in a way that's not being done currently. And I'm not trying to undermine what they already are doing, because this is something that's been ongoing for the last 30 years. And so how do we continue to make it more efficient? And that's where the benefits of this data is really during the low flow years, during the high temperature years, how do we get an extra 2 weeks of cold water? I mean, that's where, if you can get a 2 to 5% more efficiency through the season, so that you can get an extra 2 to 4 weeks of cold water coming down, that might be the protection of downstream reds. That might be the protection of, the survivability of an extra 10% of the fish, of the fry going downstream. So that's really what we're talking about with the benefits of this data. And then it also allows us to sort of categorize different years, where, we're really talking about, and this is really what it comes down to, is, it's this idea of multiple competing flows. You have flows for electricity, you have flows for the settlement contractors, you have flows for the fish protection. And how do we balance that? And it's a very delicate balancing act. When we turn around to the settlement contractors and say that there is no water coming down for them because we need to protect fish, that represents people's livelihoods as well. And so it's how do we balance all three of those at the same time? It's a question that causes consternation for everyone every year. So that's.
Yeah, I think it's a tricky question, but it lends importance to the fact that this is applicable downstream. This is applicable across years, and just building out that confidence, and even just 2 to 5% of improvement would be useful to managers. So yeah, I'm appreciative of that. I think you also got a question about what mitigation steps could be done to address leakage after quantification, and Tricia Lee had asked that question. It seems similar to what you just were describing.
Well, actually, can I add a bit more to her question?
Sure.
So I'll just do a quick plug for CFD modeling, so computational fluid dynamics. So when the TCD was originally built, there was an engineering report where they did a CFD design, basically a flow design of how water will flow into the structure. And so one of the things is that there's a physical mitigation steps that we can make. You could do a repair. So if you could get divers in the water that could actually repair a broken louver or a broken operation, that is something that we could do physically. We could also try modeling it and try modeling the hydrodynamics of the system as the water comes into the system. But we can also model with more modern computational techniques. We can model the entire system with known areas that have failed. And then that would better inform the way the structure is operating and during different flow conditions. And now with better, more advanced CFD techniques, more advanced computer clusters than we had in the mid-1990s. We have a lot more modeling tools than we've ever had before in history. And I hate just glibly saying, oh, machine learning, or oh, artificial intelligence, but these are tools that are coming online that could help feed these modeling efforts. And so how do we incorporate these tools is really one of the ways that we can use to help get that extra 2 to 5 to 10% of operation. So.
No, that was a great follow-up answer. Thinking about these sort of things you found, these small delta 2 to 5% could make such a big difference and so on. I'm wondering about, there was a question that came in about how you work in so many other systems. Have you seen similar dynamics? You had some reverse flow examples and things like that. You see this in other systems, and how does this work that you just did apply to other systems that you work in?
Well, I work in lots of different lakes. I will say doing a withdrawal envelope is something that I have never tackled before. And very few people have. And that's partly because the flow rates that are coming through Shasta are some of the biggest that we see through a dam. It is an enormous structure. And a lot of people that work in this space are actually usually working in inflows and the plumes coming in, and as the plume diffuses out from a river inflow. So looking at how sediment is being dropped down, or how contaminants are being put into the bottom of a lake. But the idea of looking at these sort of reverse problem, the withdrawal envelope, is something that, there's some initial work done in the 70s. That theory that I quoted is some very early sort of theoretical views, but very, very few people are actually working on this. So in terms of applicability, the applicability is partly in understanding the structure. The other challenge with this is that there are a lot of different styles. So the TCD itself, with this big louver system, is a fairly unique temperature control device. So some other temperature control devices we talk about, there's one at Folsom that has a tower, but the tower operates as a single tower that sort of moves a column up and down to let water through. There are also thermal curtains that are being put in around the state that people don't really understand how these thermal curtains work, and they're also much more prone to tearing. And so there needs to be modeling efforts around these thermal curtains as they're being adopted. And then there are examples from other countries with similar climates, like Australia, Spain, that are trying to put in temperature control devices, but each of them are relatively unique. So we have to consider each system, and both the setup of what the system is, the setup of what the hydrological conditions are, and then the setup of what temperature control device they're proposing putting in to protect it, to protect that cold pool management.
Great, thanks for that larger perspective. I think we're ready to move back to housekeeping, or do we have any more questions that, Dylan, are you going to take it from here?
I guess I was curious because it sounded like you might have had some questions for the previous presenters. So if you wanted to ask questions of each other, that just wanted to make sure that there's an opportunity for that, or if there are any just like broader questions from the audience. Both really thought-provoking talks, so.
Let me ask one last thing. Do you have anything you want to chime in with, Alex, before the that you didn't get a chance to say that you wanted to before the end?
Nope, I'm good. Although, Malte, I'd love to chat with you at some point about your work downstream. So
Yes, that would be really nice.
Yeah.
Let's do that.
The exit poll just popped up, so please provide your feedback. And just wanted to say thank you again to everyone to spend your time with us and engagement, and thank you so much. Really appreciate it.
thank you, and thank you for organizing.
Thanks. Yeah, these talks will be posted on our the council's YouTube page for future reference as well. So just wanted to mention that. Thanks again. All right, take care, everyone.
Thank you.
Thank you.
Bye.
Bye.
Okay, let's take a look at the last slide if we can, the what's coming up in next week.
Oh yeah, great idea. Thank you.
Yeah, no worries.
Yeah.
I know I'll be there. It's so it's Wednesday, June 12th, and it's going to be focused on multi-benefit wetland habitat and Delta food webs. So a focus on restoration, sort of, you know, what's possible with wet food webs. And the speakers will be Dennis Baldacci from UC Berkeley, and Peter Hernes and Brian Bergamaschi. So Peter from Davis and Brian from US Geological Survey. So that will be a week from today, same time, same place. Hope to see you then. Perfect last slide. Thank you.
Thanks again.
Everybody, stay cool.